Hi everybody. Today I wanted to compare the shapes of different scenarios, and I wanted to show how these individual scenarios look differently on an acceleration time graph, a velocity time graph, and a displacement time graph. And the key here is these are going to be the same scenarios for all three graphs, but they'll produce a different appearance on the three graphs. So let's just take, for example, a very straightforward one. Let's take an object at rest. I'm going to write that in some darker marker for you here. Let's take an object at rest, and we'll say, well, what are these graphs going to look like for an object that is just simply sitting still here? Let's say, for example, it's this marker at rest on that stand. And we'll look at me, and I'm a certain displacement away from that marker. So we could say it's relative to me. An object at rest, well, what is the acceleration of that object that is sitting there still? It is 0. And it stays 0 as time passes. Object at rest, very straightforward acceleration graph. It is not moving, and I'm assuming it's continuously at rest. Same thing for our velocity here. The velocity of this object would also be 0. It is simply at rest, it is not moving. The displacement time graph is the only possibly non-zero one. It just stays at a certain position away from where you start. So if, for example, it's, let's say, 1 meter away from the initial position or away from the reference position, if it's 1 meter away, well, you would say it's 1 meter away and it stays 1 meter away. So we have a constant horizontal line there for our displacement time graph. Of course, the physical significance of the graph does come into play here and tells us some things here. First of all, the slope of a displacement time graph, change in y over change in x, is velocity. So we'd say to ourselves, well, what was this slope? This slope was 0. And that's great, because it told us our velocity was 0. I'm going to put that above the line so you don't think it's area under the curve. The slope here is 0. And if we look here, well, the velocity had a value of 0. And then we can look at this slope. And we say, well, this slope, change in y over change in x, was again 0 meters per second over seconds, which is 0 meters per second squared. And that tells us our acceleration, because the slope of a velocity time graph is acceleration. And again, the value here was 0. So we see how those are all consistent, and the slope is what helps us move from one graph to another. The slope of a displacement time graph is velocity. The slope of a velocity time graph is acceleration. The slope of acceleration actually does not have a physical significance in our class. It's something called jolt, if I remember correctly, but we're not going to deal with that. Object at rest. Let's look at our next scenario. Object with a constant positive velocity. Let's look at our object with a constant positive velocity, and it's always easiest to start with acceleration here. We'd say, well, what is the acceleration of this object with a constant positive velocity? Constant velocity is a phrase we talked about. And if you have a constant velocity, we know our acceleration is 0 meters per second squared. So for this object, acceleration time, 0. Velocity time, now we said it's a constant positive velocity. We would say, well, that velocity is constant. It's moving at a constant rate. This would be like a car on cruise control, where it's just staying at a certain speed on the highway the whole time. So we'd say, well, our velocity here is going to be constant, unchanging, but positive. It is moving. This is an object that is moving, like a car, again, on the highway on cruise control, just going at a constant rate. Notice again, our slope here is 0, because our acceleration is 0. Our slope here is 0 because acceleration is 0. And again, that's change in y over change in x. Always, the slope of a velocity time graph is always your acceleration. And let's continue. Displacement time. Well, this one is a little bit trickier. And we'd say, well, the slope of a displacement time graph is velocity. What do we notice about this velocity? It is positive and constant. So we need a positive, constant slope. A positive, constant slope creates a linear function. And whatever the slope of this function is, would be the velocity of the object. And you could find that slope y2 minus y1, x2 minus x1, change in y over change in x. Pick any 2 points for that and you'd have your answer. Those are our first two scenarios, object at rest, object with positive constant velocity. Now let's look at our third scenario, an object with positive constant acceleration. This object is speeding up. An example of this might be something in free fall. And the one I'm going to do right now would be free fall if down was positive. I know that's a little bit confusing. Free fall if down was positive, or positive constant acceleration. This is an object speeding up, but speeding up at a constant rate. It's getting faster and faster and faster. Let's look at the acceleration versus time of this object. An object in free fall, for example. Does the acceleration change as time passes? And you might check the front of your reference table, and you might notice it says the word constant in front of it, and you might realize, no, acceleration does not change. Velocity changes, it gets faster. Displacement changes, it moves. But acceleration is constant, 9.81 meters per second squared. So, our acceleration here is going to be a constant positive value. I know I said to define downwards as negative. I know this is not consistent with that. But I'm just using this as an example for positive constant acceleration. If it's easier for you to think of, you could think of a car speeding up where you're very consistent on your accelerator. That's also fine. So object with positive constant acceleration, acceleration constant. Fantastic, easy, straightforward. We notice here, this is a positive constant value, which means our velocity time graph has a constant positive slope. Constant positive slope, what does that look like? Linear function. The slope is going to be a positive value. The slope is acceleration. So here we have a non-zero acceleration. If this was a free fall incident, you would have an acceleration here and a slope here of 9.81 meters per second squared. That'd be how much it goes up every second that passes. So we have our acceleration, we have our velocity, now we come to our displacement. Displacement, this is the trickiest one. On our displacement time graph, what we want to say the slope is velocity. What's happening to the velocity? It's getting higher and higher and higher. So our slope would get higher and higher and higher. You might start out with a slope of basically 0, and then it gets a little bit higher, and the slope gets a little bit higher and a little bit higher, and we notice we create an exponential function. If you have a curved line on a displacement time graph, that means the object is accelerating.
Good morning, Zavarian.
Oh no.
It is now 8:20 and just wanted to remind you.
We're going to close out on that, everybody.
The rosary at 8:25. You could find the link